the flow chair. Anton, you want to introduce yourself?
Yeah, I'm Anton Hasbrook. I'm a mechanical engineer for Central Nebraska Public Power and Irrigation District.
Haley?
Thanks, Katie. Haley Kessel, I'm the Director of Regulatory Affairs with Current Hydro.
And Yassi.
Yassi Saba, I'm an electrical engineer and project manager with Burns McDonnell.
Thank you all. Couple of announcements before we get into our program for today. First of all, for anyone who submitted Rising Star Award applications, we just want to extend a really sincere thank you. All the applications rather this year have looked fantastic. A lot of effort has gone into those and we really appreciate it. So the applications are being reviewed now. All applicants, whether you won or not, will be notified in mid-August of the application status. And then the formal winner will be announced publicly at Clean Currents in October. So more information to come on that next month. Next week, NHA is hosting the Northeast Regional Meeting, and that's going to be from July 22nd to 24th. So all Flow members get 50% off. The discount code for this is FLOW, all capital. So when you go to register, you can just enter that in and it will take 50% off your registration. For the first time ever, NHA is hosting Flow events at the regional meeting. So typically, if you're not familiar, NHA has smaller regional meetings like this one in the Northeast, and then 2 larger national events, Clean Currents and Waterpower Week. At the larger ones, there's flow specific events, but typically that's not done at the smaller ones. But that's changing this year. So at the Northeast Regional Meeting, there's going to be an early career professionals lunch right before the facility tour. That is free of charge, but NHA is asking that you do add this to your registration just so they can estimate food and seating. And then on the same day, Tuesday, July 22nd, there's going to be a flow after party of sorts after the welcome reception. So this is not a hosted event, but it is going to be it will be at the Brew Barn at the Great Wolf Lodge starting at 7 p.m. and it will go until it closes. Anyone who's at the conference can attend, but we're really encouraging Flow members to attend and just continuing networking kind of throughout the conference. So I've seen Kelly drop in a few things in the chat. There should be a link to RSVP to that event specifically. Perfect. Thank you, Kelly. And then looking forward a few months, Clean Currents is going to be in Pittsburgh, Pennsylvania, October 14th to 17th this year. Again, Flow members get 50% off. So if you are going or you're thinking about going, you can email Ellie with NHA and she can give you the discount code for that. This is a huge benefit to justify your attendance. So I think Kelly's, again, going to drop a link to a resource that NHA has drafted with kind of some practices and guidance on how to justify your attendance at something like a Clean Currents to either your manager or supervisor. So you can go to that link for additional resources. We are going to be hosting a Flow networking event at Clean Currents. That's going to be on Tuesday, October 14th from 6 to 8 p.m. at Shorty's Pins and Pints. There'll be food and drinks, and similar to what we've done in years past, there'll be bowling, arcade games, cornhole. So it's going to be a good time. Again, the one kind of nuance here is this is for Flow members, which are typically 40 and under. So you'll add it to your registration. We have in years past had people who are like, 41 or 42, but are still new to the water power industry. You're more than welcome to come. The 40 is like a soft limit. So feel free to reach out to Kelly if you're in a situation like that. Okay, I think I'm through my announcements. So one thing we've started for 2025 is industry hot topics. Seems like every day there's something in the news that's changing. So this is really our time to let Flow members kind of get a little glimpse of either a new piece of legislation, a call to action, something that's happening in the industry. So you're more educated when you're talking to clients or colleagues or your peers. So today we have Michael Purdy on. He is NHA's Vice President of Regulatory Affairs, and he's going to be providing an overview of the One Big Beautiful Bill. So Michael, I'll turn it over to you.
Thanks, Katie. Can you hear me all right?
Yes.
Great. Thanks, Jim. So yeah, so on the 4th of July, the president signed into law the One Big Beautiful Bill Act. This is basically his this is probably his primary piece of legislation that he'll be able to pass in this Congress under current circumstances, right? And so there's a whole host of things in this bill that I'm going to go ahead and set 99% of that stuff aside. But for the purposes of this industry, I want to talk about what's in the bill for Waterpower, right? And so if you take anything away from this conversation, my recommendation is go to Powerhouse, check out last Monday's article where we list all this stuff out. If you're not signed up for Powerhouse, on the right side, there's a link that you can sign up, and every Monday you'll get Powerhouse into your inbox. So what's in it for Waterpower? At the end of the day, this may seem like not a no big deal, but we really did a really nice job as an industry of playing defense here. So all of the wins that we got in the Inflation Reduction Act that allows hydropower, pump storage, marine energy to claim the production tax credit and the investment tax credit, we were able to defend those and ensure that we keep those credits for projects that commence construction in between now and 2033 for the full value of the credit. And this isn't just greenfield development. This is incremental upgrades to facilities, repowering existing facilities, so on and so forth. So this really helps lower the cost of these types of investments. Why do I say it was a really a big win to maintain these credits? Solar and wind got slammed. I'll just be blunt. They lost a significant amount of the value of their credits. They have to commence construction really by the end of next year to have any value. And on top of that, it sounds like the administration is going to be working towards making it even harder for those technologies to claim these credits. And those technologies, their whole industries were built off of those credits. So really being able to play defense and ensuring the fact that we are able to claim these through 2033 really is a win. It didn't start that way, though. And this is where I got to give a lot of credit to the NHA membership. When the House introduced their bill back in May, we were dead to rights, frankly. The House's bill really got rid of all the credits or made it so burdensome to comply that we never would have been able to comply in the first place. But through the concerted advocacy of NHA member companies, the industry, NHA staff, we were able to get the Senate to a point to ensure that our credits stay them. There's some wrinkles around certain policies, which are called foreign entity of concern. I won't go into those here, but for the most part, I would say we kept basically everything that we already had through the Inflation Reduction Act. What comes next? Now we're turning into implementation. So whereas Matt Allen and Brittany May spent a lot of time on Capitol Hill lobbying Congress, it's now up to me and my team to use our resources, use the industry to ensure that the implementation of this goes swimmingly. Just want to give a few quick thanks. A couple of members and a couple of companies really leveraged our voter voice tool in order to protect these credits. Current Hydro in particular did a really nice job. HDR, Kleinschmidt, UBC Millwright. So without the concerted effort of you guys reaching out to your elected officials, we would not have been able to play defense. So that's the nuts and bolts of it. Katie, I may have gone over time there, and I know that was quick, but anything else I can add?
On time. So thank you so much, Michael. If folks have questions for Michael, feel free to add them in the chat and we can make sure they get back to him. So thanks again for your time.
Sure thing, Katie. And if I may do a quick plug, after this call, NHA is having an overview of the One Big Beautiful Bill Act, and then the things we're going to focus on implementation. So if you want to be part of that, if it's not on your calendar, shoot me a note and I'll forward the invite.
Thank you so much. So the purpose of today's call is Hydropower Anatomy 101. This is something that, depending on where you get plugged into the industry, you may never or very rarely get out to an actual hydropower plant. So we thought it'd be beneficial to just give a quick overview of what type of equipment make up a hydropower facility, and then how that electricity actually gets generated and then transferred to the grid to then going to consumers. So today we have two great speakers, both of which have been part of NHA's Hydropower Systems Principles training. So that's been brought up often on these calls and throughout NHA's marketing. They are offering an 8-hour overview as part of the Hydropower Systems Principles training at Clean Currents in person. So that will be in October. And there'll also be a 40-hour virtual NHA certificate course starting in November of this year. So this will be a little bit of a preview into the topics that are covered in that training. If you're interested or you want more training, those are two great resources to look into later. So our first speaker is Jim Thrasher, a consultant with Thompson Construction Group, giving kind of the equipment 101 of Hydropower Anatomy 101. So Jim, I'll turn it over to you.
Okay, thank you, Katie. And I will speak for a few minutes of introduction. But first, there was a huge void in the hydro industry for years on knowledge transfer. And if you attended Clean Currents or Hydrovision or CIATI, practically any event that was oriented in hydropower, you heard about knowledge transfer and the lack thereof. And everyone said that we needed someone to present the information because we weren't mentoring people like we used to 30 years ago, where you would shadow someone for 2 years before that person retired. So the tribal knowledge was being lost. And so we knew that there's someone needed to start teaching a course on the basics of hydropower. And finally, NHA heard our plea, the industry's plea, and now they offer this course. So you're going to hear a brief from Jay and myself today. Jay teaches water to wires. I teach the equipment engineering and technology. There's 8 modules total. The other 6 are asset management, dam safety, markets, production planning and water management, licensing and compliance, and environment. So we pretty much cover the hydro industry. Like we do it in an 8-hour course, and we also do it in an expanded 40-hour course for those who want to get more in depth. So what I also wanted to pass on that for those entering the industry, you're doing exactly what you should be doing, and that is getting involved in as much with the NHA as possible. The networking that you will and friendships that you will form here will be lasting a lifetime. And if you run into a question at work and you don't know where to turn, this networking becomes very valuable, especially when you go to events like Clean Currents, where they have an exhibition hall and all of the vendors are there, and you can literally walk around the floor and meet them and just take their business cards. And in the future, when you encounter an issue with something, you can go through your Rolodex index cards, or if you put it on electronic form, we're all willing to talk to you with a phone call. We're very eager to give away information. It's not like a lot of industries where nobody wants to talk about it and it's privilege. We like to share what we know. So you're doing exactly what you should be doing. So my background, I went to a military college and had a 4-year military obligation, and I entered the Marine Corps after graduating as a civil engineer. In the Marine Corps, I was a logistics officer and a combat engineer. And after finishing my service in the Marine Corps, I joined an investor-owned utility, American Electric Power, and I started out in the hydro group, and I remained there for 31 years. So my entire career was in hydro, and I started out as a dam safety engineer, and I went into project engineering, then into managing hydro plants, operations, then went into the capital and O&M maintenance, and managed that to the end of my career. After retiring from them, I joined Thompson Construction as a part-time employee doing consulting work in the fields of turbine disassembly, reassembly, some of the dam safety stuff, some of the civil work. So that's what I'm doing now. So at this point, I'm going to try to share a PowerPoint. Okay, can everyone see that?
Yes, we can.
Great. Okay, so which one do I do for start the PowerPoint presentation? Just do that? No?
We now see the model overview slide.
Okay. Okay, so let me go back to the title. So you're seeing the title, which is Equipment Engineering and Technology. So, gosh, I hope that's not, okay. So this is the title page, and what we try to do with each course is we give a module overview. What do we expect for the student to obtain from this course? And we summarize that with this slide. Learners at the end of the course will be able to name the major equipment in a hydro facility, and they'll understand the high-level purpose of the major equipment in a hydro generation system. So that's the goal. And like you were saying earlier, we're going to talk about the large equipment in the hydro plants, and then Jay will get into more of how that converts into how we use that equipment to make electricity. Okay, why is this not? Okay, so I'm going right into this. This is the full course, and I'm just going to hit the slides that are of interest today. So dams, gates, spillways, water facilities, that's getting into the civil side of the equipment. And we talk about what kind of dams are out there. What do they do? Well, they're a water blocking device that diverts water normally into a powerhouse. These dams are usually concrete or earthen embankment. They are gravity dams or arch dams. And we see that in this next slide. You'll see an arch dam, an illustration of an arch dam, which is a little cheaper to build, takes less concrete. It relies more on the abutment for stability than it does just for the weight of the concrete itself. So we talk about arch dams and how they function. We talk about gravity dams. We get into roller compacted concrete dams. We talk again about embankment dams and berms. And then we progress from there into intake gates. The intake gates are gates that control the water into the turbines. So we talk constantly about the path of the water flow. So water's traveling down the river. The first thing it encounters is normally a debris boom or a boat barrier. Boat barrier, then the debris boom. It passes beneath the debris boom, goes into the intakes, goes through intake racks into a penstock, flows through, and that's what you see here is the penstock. It flows through a penstock into the scroll case, and from the scroll case through wiki gates, and spins a turbine. A turbine is attached to a shaft. The shaft is also attached to a rotor. The rotor spins in a stator, and that makes electricity and goes out onto the grid. So that, in a nutshell, is the flow path of water. The water exits into the tail race after passing through the turbine. So this slide, we talk about what do you do with the debris that's on a river. And the slide to the far right, that's what Norbert is very familiar with. It's a debris boom, and that boom catches floating debris. It can be man-made or natural. Most of what you see in this slide is natural. At the downstream side of that boom, it normally attaches to a gate. That gate is called a trash gate, or it can be a spillway gate. And that's how you pass keep the trash out of your intakes and pass it on downstream by opening that gate. To the far left is trash racks. So the debris that makes it past the debris boom gets caught on trash racks. The trash racks are right in front of the penstock. So when you catch it, you have to do something with it. So you have trash rakes, which are in the center. And the trash rake removes the debris from the intake racks, usually dumps it into a trough directly behind the intake racks. And that trough is flooded with water, which takes it into the tail race. So that's how we deal with, those are some major pieces of equipment that you'll see on a dam, and it's very important because trash is a problem at almost all dams. This is a typical run-of-the-river plant. It usually has a water blocking device, a dam of some type, at a location on the river. It diverts water through either an open channel flow or through an above ground penstock, which is this one is an above ground penstock. That water goes into the powerhouse and flows through, like I was telling you earlier, the intake screens, into the penstock, through the turbine, and eventually out into the tail race. The area that is bypassed in the river, this flow area here, that's called the bypass area, and that's where environmental rules and your FERC license comes into play, because you have to meet minimum flow. You can't just divert all the water into your powerhouse. That channel has to keep water in it for aquatic purposes. So spillways, we give this as an example. This is Oroville, and I'm not going to play it because of time constraints, but we talk about spillways. And spillways, the purpose of a spillway is every dam or every powerhouse has its own hydraulic capacity. So let's say that a powerhouse has 2 turbines, and at full load, each turbine requires 500 CFS, cubic feet per second of water. So we would say that the capacity of that plant, the hydraulic capacity of that plant is 1,000, 2 times 500, 1,000 cubic feet per second. And that, if the river inflow is greater than that, and you can't pass it through your units, it exceeds your hydraulic capacity, you have to spill it. And we do that through spillways. I'm going to do that. Okay. This, we have a schematic that shows, I'll see if it'll play. This shows the flow of water through a hydro site. It gives you an idea of what I was talking about earlier. Water's flowing through the penstock, hitting the turbine, spinning the stator or the rotor, and then spinning in the stator, and that creates electrons going out into the transmission grid. Well, okay. Then we talk about Bernoulli's equation, and we simplify that down to power is equal to N times rho times Q times G times H. To simplify that even further, that breaks down to power, which is in kilowatts, is equal to N, which is the efficiency of the turbine, times Q, which is the flow in the river, times H, which is the head, the difference between the forebay, the pond, and the tail race, divided by 11.81. So theoretically, any hydro site you go into, you can calculate what its nameplate capacity could be under perfect conditions. And that's where we start when we're working with a plant, trying to determine whether or not that site is optimized. And I think we have, and these are turbine shutoff valves. And they are another means of blocking water going into the turbine for maintenance purposes. Sometimes you have head gates or intake gates. Sometimes you have turbine shutoff valves. And I think I'm going to go into the major turbines. We talk a lot about turbines, and there are three major types: the Francis turbine, the Kaplan turbine, and the Pelton turbine. About 60% of the turbines in the United States are Francis turbines. They are typically in moderate head, up to say 600 feet in head. A Francis turbine is fine. A Kaplan turbine is made for sites where you have a lot of flow in the river, but low head, somewhere in the 20 to 30 feet of head, but lots of flow. A Pelton wheel is used where you have little flow, but lots of elevation, so lots of head, usually in excess of 1,000 feet. You normally see these in the mountains. In the continental United States, you'll see these in the northwest part of the U.S., in the Smoky Mountains of Tennessee, North Carolina, and Alaska. I'm going to go over that. There's a cross section of showing the rotor and the turbine, how the turbine is attached to a shaft, which is also attached to the rotor. And we talk about the types of bearings that keep this aligned and take the thrust load. So at that point, I think I'm going to close. Throughout this presentation, we also have knowledge questions that are necessary, because if you take this course, you get continuing education credits if you're an engineer and you need those. So in order to qualify for that, we have to do testing throughout the course, and that's how we do that. Are there any questions, or should I think the agenda called for me to just close and let Jay take over? Is that what we're doing, Kelly?
Yeah, if you have time to stay on, Jim, we can just do questions at the end.
Okay, that's what I'll do. So I will stop sharing, and Jay will be on.
Thank you so much. Yes, our next speaker is Jay Anders, a professor at Southern Adventist University. So Jay, I'll turn it over to you.
Great, thank you. Like Jim, I'll click a few buttons here. Probably embarrass myself, not intentionally.
No, that's normally me, Jay. You don't do that. That's
Please, Jim. Please. Let's see. All right. I hope everybody's seen a screen that says water to wires. Again, my name is Jay Anders. Some of you I've met, some of you I haven't. Jim and I have been friends for years. You know, like he got a great overview of what the class is. You know, we get together and, you know, Jim, I was sitting here as you were talking. I was thinking, man, you know, we get together and we teach this stuff in an hour, and now we're condensing it down to 20 minutes. So we're really throwing stuff at you really rapidly. You know, the group has such a diverse background. I heard one person say they were electrical engineer. Go electrical engineers, by the way. But obviously, you know, I know we have environmental folks. We have, you know, civil, mechanical. When we give these talks, we're talking to the broad audience, and there may be some of the sessions you're like, oh, I know all that. The great thing is you probably don't know all of that, but yet still over the course of the full day, there'll be so many things you end up learning in the other sessions that we go through, like the 8 different modules. The water to wires, it really is the real overview of the class. We sort of set it up, we go through the history of what's going on with it and everything, but it really, like I say, Jim really gave us a great overview. I guess I'd start off with sharing, much like Jim did, a little bit about, you know, who I am, what I've done. Much like Jim, I started off in the military, graduated high school, and went off to the Navy's nuclear power program. Spent about 8 years in the nuclear Navy on a submarine, cruising around the world. My career was, I always say, I was fully immersed in the hydro world before I ever became a hydropower engineer. Started off in, like I say, the nuclear side of stuff, was an electrician in the Navy. As I got ready to get out, I saved money, met a wonderful young lady that would put up with me forever and still does. And I started going to engineering school at the University of Tennessee at Chattanooga, got my electrical engineering degree, interviewed with the Tennessee Valley Authority. I thought, man, this is great. I'm going to go do nuclear power at TVA. And all of a sudden I get my job offer and it says, yeah, you're going to work in the hydro engineering part. And I thought, well, okay. You know, it was 1993. The job market was as bad as it probably is now. And so I was thrilled to get the job, started at TVA. And again, in their design group, the TVA was modernizing all their units at the time. We were, putting in new turbines, all new electrical equipment. It was a great time to be a design engineer there, and did that for about 15 years. After that, I went off into the consulting world, worked for a couple different consulting organizations. Black and Veatch was by far the biggest one I worked at. I led projects there from, one coast to the other. Did work in Carolinas, California, obviously, Alabama, up here in Alaska now. Just really got to do projects just all over the place. The last couple of years, I worked for Rye Development as they were looking to develop some run-of-river plants, and then an opportunity came up to start teaching at a university, which is about 2 miles from my house. My wife graduated from there, and my daughter attended there, and she only got a chemical engineering degree. And so, they had a chance, and it really sounds like fun. So I just started teaching at Southern. I've been there 2 years now. Our first class graduated last year. It only had 4 students in it because they were ones that had an associate degree. And all 4 of them for the engineers group passed the fundamentals of engineering exam. Really proud of them for doing that. Also, I'd share, I was, the fact that you guys are on this call, and I know Jim complimented you for it. I want to do the same thing. You're where you need to be. Getting on these calls, being a part of Flow. Flow wasn't a thing when I was your guys' age, but I would go to, all the NHA regional meetings and national meetings, and just got really involved. I chaired, oh man, I forget all the different groups. The small hydro group, I was a part of that. The technical group, I was a part of that. Really, all the technical things at NHA is really where I sort of leaned. But eventually, became the treasurer of the organization. And back during the years of COVID, I even served as our chairman for a couple of years. So I'd encourage you, stay engaged. You'll meet a lot of wonderful people. You'll learn a great deal of things. And again, like Jim was noting, you'll have somebody to call when you have a question, and you will inevitably have questions. So anyway, this is a little bit about me, a little bit about where this module goes. It really helps us understand how do we turn water into electricity. So I wanted to start off just asking a real quick question. Oops, I shouldn't have done that. All right, maybe just pretend like you didn't see it. Maybe you didn't. But think about hydropower. What are some things that come to your guys' mind as, hey, this is cool about hydropower. This is a real benefit of hydropower. And we have a little chat box, so feel free just to, start typing away, act like you're listening to me. It's kind of like we have engagement. And I actually think I'm in a classroom with people. I may say it's a lot more enjoyable than these Zoom meetings. I got very tired of Zoom meetings during pandemic. In-person meetings are pretty wonderful. Again, that's why I encourage you, go to in-person meetings when you have them. But anyway, benefits of hydropower. Kelly, you're going to have to tell me, because in this sharing mode, I don't see the chat box, but is anybody put anything out there? Could anybody read some of the benefits, or just shout them out loud? You don't have to type, Go ahead and talk to me. That'd be fine.
We have a few so far. Creates recreation areas. It's renewable power production that can be planned ahead and is not as volatile as wind and solar.
Yeah. No, those are all outstanding ones. And for the sake of time, I got to keep rolling. We share just a quick list. And again, this is just yet a partial list, isn't it? I mean, there's many things. And again, like Jim, I worked in the industry for 30 years. I don't know that I'm necessarily biased. I do think we need all forms of energy production: nuclear, solar, wind, hydro, fossil. When I say fossil, the thermal plants, we need all of them. And if we start eliminating all or a few of them and just focus on one or two energy, it could get really challenging for the grid. And we talk a lot about the grid and how hydro helps balance the grid, but here's just some quick ideas. Again, our time is short. We must march forward. Jim gave, a bit of an overview, and his background is the mechanical civil side. Mine is the electrical side. And I really wanted to, as we start talking about how do we get electrons out of the water and get them out onto the grid. And believe me, some people think that's what they do. They think a dam is a big screen out there, and we're screening the electrons out of the water, and there's less downstream, and the fish don't like that. None of that's true. You all know that. Well, we have, as Jim talked about, we have that penstock. That water is flowing in. It's behind our dam. That dam, it creates this difference in elevation. That difference in elevation, what we have is that potential energy. We get to the physics side of what's going on here. The water behind a dam is higher than the water in front of the dam, the downstream portion. We get that difference in elevation. You get gravity acting on that higher elevated water. It wants to go to a lower elevation. That's how they have that potential energy. It's just sitting there waiting for the wicket gates to open. When those wicket gates open, we have that potential energy. Now that is starting to transfer itself into kinetic energy. That water starts moving. That kinetic energy now goes and hits the next thing Jim talked to us about was the runner. So now we have let me put a little button here. Oh, this will be wonderful. Yeah, so we have that water coming in through the penstock here, and we open these wicket gates now. The wicket gates, they're just a big valve. Think of them as a valve. We open that up, and it's a controlling type valve, though. We have the governor that's in hydraulic means that we open these wicket gates. They control the water that hits this turbine now. So now I have potential energy. It became kinetic energy. It starts hitting this turbine. Now I'm creating mechanical energy. This turbine is going to start spinning in circles now. Well, as that turbine spins in circles, it's connected to a shaft. The shaft goes on up. It's connected to my rotor. The rotor is the rotating portion of my generator. The generator is composed of two basic components. Yes, there's a lot more to it, and I could spend a lot more time talking about it. But we have the rotating portion of the generator, the rotor, and then we have this stationary part of the generator. There are two very large electromechanical items. We're spinning the rotor. The rotor, we connect through our excitation system. We put some DC power onto my rotor. It now becomes this really huge magnet. It's spinning. My stationary winding, it's sitting there. Now, again, I don't get too much into the physics side of it, but we have some brilliant people back in 1800s that learned, hey, look, if you have a magnet and you move a wire through it, you actually get electricity flowing. We get this potential of energy created. What we did here, we put it backwards. So we start spinning our rotor, and we let the stator stay stationary. We control the amount of voltage on my stator from my exciter. And then ultimately, though, the stator winding, it now connects to my generator leads, which ultimately go on out and get my electricity moving on to the grid. I want to go to this next quick, some of the things you hear about. You'll hear about a generator circuit breaker. Well, a generator circuit breaker, it's a light switch. It's just a big old switch, on, off. Yeah, we have a lot of cool things that make that happen. We have all this protective relay and stuff. Sometimes it just switches. The operator, he'll synchronize the generator to the grid. He'll make the generator be in the exact same phase relationship. We'll always hear about three-phase systems, A, B, C. He'll make sure that the rotation of our generator is exactly the same as the grid. Make sure the voltage is matched really well, because we don't want big arcs and sparks when we parallel. And then make sure that the frequency is also well matched. That way, as soon as we bring it online, it'll pick up a little bit of load. Go back to those wicket gates. As we keep opening those wicket gates more and more, we can put more and more load. And you'll understand that, right? It's like if you're pushing your car with your good friend when you ran out of gas. Your good friend, he goes to the gym all the time, big burly fella. He's working like anything pushing that car. Well, you could lay your hands on the back of that car. You could wrinkle your face a little bit like you're really pushing, but in reality, maybe you're just leaning on the back of that car. You're still going the same speed. You're still going 60 hertz. One of you is working really hard. One of you is not working very hard at all. That's the idea of what we're trying to do, is matching my frequencies. So that's what this generator breaker, it connects my generator on out to a generator step-up transformer. Maybe you've heard of that before, the GSU. So I go and the generator step-up transformer, what it does, our generators typically generate, at what we call the medium voltage range. Some of you think medium voltage range is high, but this is like less than like 15,000 volts. A lot of generators are around 13,000 volts. Well, they're generating at 13,000 volts. The grid is, 161,000 volts. Maybe it's 500,000 volts. So we have to step up that transformer. Step up that voltage. All this is a whole bunch of windings, and they're parallel to one another. And the voltage that it goes up, it's just a ratio of those windings. If you bring in 1 volt as a 2-to-1 ratio, you get 2 volts out of it. Well, what we do, again, we'll bring it in maybe 13,000, send it out at 161,000, and now you say, what's the why? Why would we do that? Well, the why is current is inversely proportional to voltage. So as we step up that voltage, the amount of current out on the grid is less. So we have less what we call I squared R losses. We have less power losses out on my grid. So that's why we have this generator step-up transformer. So we come out of my generator, we go to my generator breaker, we go to my step-up transformer, and ultimately I get out to the grid. Now how about a little bit of a cartoon here, kind of tying together Jim and I's whole talk that we've done here over the last few minutes with you. This is just a very conventional hydro plant. This is one like a lot of you've seen, maybe visited as a kid. Big old piece of concrete. It's just the weight of that concrete smashing down on the ground, keeps this thing from sliding, from tipping, all those things. People like Jim do all these great calculations, all of our dam safety people, all those wonderful things that they are looking at. So that's just it. We have this higher elevation back behind the dam. On the downstream, we have this lower elevation. And then Jim talked about the trash racks, the intake structure, all that structure that the water has to flow through to ultimately come down to where my turbine is resting inside this pin stock coming down to my scroll case. And you can see how that we start spinning. And this shaft connects right up to my generator. The generator now, it starts spinning. Have these generator leads that go over to my step-up transformer. So I go from my 13,000 volts, maybe up to 161,000 volts. It goes out to my out to the grid, and ultimately to everybody's house. Now, a lot of things we hear about nowadays are pump storage plants. And so, again, I just want to quickly touch on pump storage plants, how we connect them to the grid, because they are similar but different, right? It's a quick view of a pump storage plant. Now, again, you think about, here's my upper elevation, my upper pool, like we have at a normal hydro plant. We have my lower elevation, again, very normal. So you can see we're still relying on that potential energy. Down here in my little powerhouse, I still have a generator. It still has wicket gates, turbine shut-off valves, way to stop all of this water from coming down here, way to I can control it. We still need generator breakers. We still have the idea of the transformers stepping up that voltage. And a lot of these plants, so they're going to, my generator leads, that's this dashed line you might be able to see, takes it back up to the top of the transformer, and excuse me, the top of the mountain. And a lot of times we even have another switch yard up here that'll step up even to a higher voltage. There's our switch yard over in this corner. So maybe down here, you'll do it, initially step it up. Because this elevation for a pump storage plant, the sheer elevation is like over 1,000 feet. So that's just in the vertical direction. And then you got the run of this cable and everything. So what we'll do, we'll get up here on top and maybe we'll step it up to 500,000 volts. Now, again, same, just another step up transformer, a little larger, a little more involved. But, again, it still gets us out, ultimately connected out to the grid and ultimately come to your home and my home. So that's a real quick overview of how we get the power generated and how we get it from our hydro plants, whether it be a conventional or pump storage, how we ultimately get that power out on the grid. So I will pause here, stop my sharing, and allow us to maybe have our question and answer period.
Thank you so much, Jay.
Yeah,
so feel free, folks, if you want to just enter your questions in the chat, or feel free to come off your mic and turn your camera and you can ask that way.
I can start. I have a question for Jim on Kaplan turbines. Jim, you mentioned that you typically see them at lower heads. I've always understood Kaplan turbines to be very effective at changing heads due to the ability to control the blade angle on them. So I don't have a specific question for you on that. I was just hoping you could comment a little bit on the flexibility of Kaplan turbines.
Yeah, the Kaplan turbines are one of my favorite turbines. And unfortunately, the slide I showed you was actually, they called it a Kaplan, but it's a propeller. That's what was shown in there, which is a fixed blade. But the Kaplans, the blades pitch and they can adjust to changes in head. It gives you a lot wider range of operation. It does great with combating cavitation. So yeah, it gives you a wider range over those low head facilities, which optimizes the production of the plant.
Yeah,
Perfect.
that's interesting. Yeah, it's interesting, Jim. You know, I saw a lot of Kaplans we had at TVA, and well, we put them in thinking that the pools were going to change and elevations were going to be, you know, changing and everything. But in reality, you know, as the environmental side came along and we started focusing a lot more on that, we stopped having those big changes in elevation, and we went in and thought, okay, if these are the pools we're going to operate at, we actually, much like you're noting, we made them a fixed blade at that point. We said, okay, this is how we're operating the reservoir, so there's no need to change them. And again, because the Kaplans, right, they have the oil going to them. I think there's other mediums they're using nowadays, but you know, different things to think about. But yeah, great topic. We could probably both talk way too long on it.
Yeah,
Jim,
from an
you
environmental
mentioned-
standpoint, they have the hubs are full of oil, and if you have a trunnion seal where those blades pivot, if you have a trunnion seal go, you can get oil in the water. So a lot of folks are going away, like Jay's saying, going to the fixed, to the propeller style, or to another turbine style entirely. So
Yeah.
we're all very sensitive, and our environmental module goes into that in detail.
Oh, excellent. Thank you both.
I'm just hoping, you mentioned cavitation, and I'm not sure if folks on the phone know what that is. Could you give a quick summary of what cavitation is?
Yeah, that's for the Navy guy, but I'll tell you the hydro view on it is that as the turbine spins in the water, it creates bubbles, and those bubbles burst, and depending on how they burst and what the design of the turbine is, it can actually cause corrosion or pitting in the metal of the turbine, which enough erosion will cause section loss, and section loss leads to turbine failure if you do not stay up on it and repair it. So as a former submariner, that was cavitation was a cuss word in the Navy, I think.
No doubt. We weren't so much worried about the damage it caused to the prop. We were more concerned about people knowing where we were and then trying to damage the entire submarine. But
Yeah,
certainly, yeah, what you're talking about, Jim, it's a mess. Cavitation at the hydro plants, a major maintenance issue, as you know a lot more about than I do. Clearly, with all your operations time.
Both. Haley, I saw you came on camera. Do you have a question?
I do. Jim, I was hoping that you could repeat the power equation, please. Being a power producer, I think this is something I should know. I didn't catch
Okay.
all the variables in that.
Okay. P is equal to NQH divided by 11.81. P is in kilowatts, power in kilowatt hours, or kilowatts, I'm sorry. Q is in cubic feet per second. That's the average flow of the stream where your hydro plant is located. H is the net head of your power plant. N is the efficiency of your turbine, which is normally in the 90s, 90 to 94%.
Appreciate that.
If it's a modern turbine.
Yeah, I've seen our spec sheets on the turbine, so I know exactly what you're talking about. And just to add to the conversation earlier, when you're speaking about oil with the Kaplan turbines, I know I've written in our applications a few times that we'll be having oil separators, and then we'll have to be permitting that permanent discharge with the state, of course, that the river is located in.
Yeah.
Thank you.
Any other questions? I'm not seeing any other hands or comments. So I have a kind of a general question on overall in all the courses, something like fish passage. Is that addressed in some of these modules, or is it more when we get into like the environmental licensing?
It is covered in the, and Betsy O'Malley covers that. And which one does she teach, Jay? Does she teach?
I think it's the environmental one. Is where
It is,
she's
it is the environmental. So yes, fish passage, fish ladders, the various types of fish ladders, even including the, gosh, what's the one where they shoot the salmon over the dam? That's included.
Whoosh.
Whoosh.
I think.
Yeah, the
Yeah.
whoosh. So yeah, and the various types of fish ladders are all included in that, and where that is in the hydro history and how it's becoming more and more prominent for plants during relicensing to address fish passage. If they weren't addressing it before relicensing, they're gonna encounter that.
Thank you. Actually, we do have a question in the chat now. What do dam operators need to do for water temperature control?
Oh, well, I'm working on a plant in Pennsylvania right now, and the downstream fishery requires a certain temperature. And so on the forebay side, they have what they refer to as temperature gates. So right behind the intake screens, they have this series of gates which they can adjust the elevation to, and it stratifies the intake water. So if they need a cooler temperature in the tail race, then the water is drawn off the bottom of the lake. This is on the forebay is a lake. So they draw the water off the bottom. If they need a warmer temperature, then they draw it off the top. And these gates are adjusted by a programmable logic controller, PLC, and so the temperature of the tail race feeds into the PLC and it automatically adjusts the gates accordingly. Yeah. So that's one example that I know. Jay, are you familiar with that? With your work in, especially at some of the consulting, you might know more.
Yeah, no, I mean, where we've seen it too is, first off, we should say every hydro plant can't do it. There are certain ones, especially the higher head ones, that have an intake at the bottom of the lakes. Even at TVA, what we would do there is we would time the release from like our Norris Dam site to where we would have that slug of cold water as it's going down the river would get to our thermal plants at a particular time of day to help them be more efficient, to help them, just run more efficiently. That's another way they do it, is just the whole timing of the water coming out of them. Realize, sometimes if you have like a big lake, Chickamauga, some of the lakes that don't have very much elevation associated with them, look, that whole lake's going to warm up in the summertime, and that's where we get into oxygen issues and a whole other discussion we'd have of what do we do with oxygen. But that's just sticking to your question of temperature. That's just a few thoughts on that.
You kind of led into another question. Are there techniques for operating turbines that would increase DO in water? I've heard of air breaker valves being used.
Yeah, Jim, you want to chat on that for a bit?
I'll touch on it first. And most of the southern plants have that problem. TVA has the problem. Duke Energy, Southern Company, AEP. We have dissolved oxygen issues in the tail race, particularly, well, in the summer months. So how do we resolve that? We try, I mean, there's lots of ways to do it, and there's lots of folks doing it different ways. But what will work every time is an air-entrained turbine, where you're injecting air through the blades of the turbine. And Voith Hydro makes an air-entrained turbine. They're actually the founders of it. And GE has one out now that's fairly recent. They came out with it about 7 or 8 years ago. And there may be more, but those are the two that I'm familiar with. I know that we tried injecting air into the tail race, air through the head cover. We never got the dissolved oxygen content we were required to until we went to the air-entrained turbine, and AEP bought theirs from Voith.
Yeah. Another thing a lot of people are doing, they're actually investing in putting liquid oxygen right in the upper reservoir. They had a bubbler system on the bottom of the reservoir there, and just purely injecting oxygen. As Jim noted, it's just really during those hot months. And you maybe a 6 to 8 week window. I realize that as our climate is different than what it was even 10 years ago. It's becoming more prevalent, and we're getting hotter in places we didn't used to get as hot. And so DO issues are certainly not just a southeastern U.S. problem that we used to have, but it's something. The thing I'd want to share is it's not a all around the year issue. It's just during those warm times of the year. And as Jim said, there's multiple ways, and there's TVA's put several papers out over the years of how to address O2.
Thank you both. And for folks on the phone who are kind of curious about dissolved oxygen, or maybe this is the first time you're hearing about it, we have done a dissolved oxygen 101, and that meeting was also recorded. So you can check the NHA portal to kind of get a deeper dive on what it is, how it becomes a problem, and ways to mitigate it. So we're actually pretty close to the end of time. So I want to thank Jim and Jay so much for taking the time to talk to us today. And then a few other just quick wrap ups. We're hoping to see as many folks as possible at the Northeast Regional meeting next week. Make sure to say hi to your fellow flow members if you see them. Now is a perfect opportunity to start talking to your manager or supervisor if you're interested in attending Clean Currents this fall. Again, if you need resources or how to pitch that for the value added, feel free to reach out to flow leadership or NHA staff. And lastly, if you're kind of intrigued from today's presentation on the Hydropower Systems Principles course, feel free to jump into the links that Kelly added in the chat to sign up for either the in-person at Clean Currents, or stay tuned for the 40-hour course that will be virtual in November. So thank you, everyone, and we'll see you next month.
All right.
Have a good week.
Take care, all.
Bye.
But also,
Thanks, everyone.
just
Thanks. Thanks, Jay. Thanks, Jim.
also for the
You're welcome.
I know I asked you for like an impossible task. Did a very good job.